Hello, everyone. Today I'll be presenting the paper Approximately Stable Committee Selection. This is a joint work with Zhihao Jiang from Tsinghua University and Kumesh Nagala from Duke University. So in this paper, we consider the problem of committee selection. We are given a set of n voters and m candidates. And we call a subset of candidates to be a committee. In our problem, each candidate is associated with a weight Si, and the weight of a committee, Ws, equals the sum of weights of the candidates in the committee. And the goal is to find a committee of weight at most k for a given weight limit k. And in our problem, the voters have preferences over committees. And we assume that each voter has a weak ordering on all possible committees. And the only requirement that we put is the monotonicity requirement. So if a committee S is a superset of another committee S prime, then every voter should weakly prefer S to S prime. The model of committee selection have many applications. For example, in these multi-winner elections, we say voter I either approves or disapproves each candidate, and we need to choose k winning candidates. And this is a classic setting in social choice. Another setting is the participatory budgeting setting, where the candidates are the public projects, and the project I has some cost Si, and it will give utility UIV to some voter V. And we need to choose a subset of projects so that the total cost is at most k. Project I can be chosen or not chosen, and the utility to voter V should be the sum of individual projects that are chosen. And the participatory budgeting elections are widely run around the world. Another model is this clustering model, where we are given some points in a space, say n of n points, and we want to choose a set X of at most k centers. And for each point, we can see it as a voter, and her utility should be related to the distance to the closest center. So in our problem, we consider this fairness or stability constraint. And the idea is every demographic of voters should feel that they have been fairly represented. And they shouldn't have the incentive to deviate and choose their own committee of proportionally smaller size, which gives all of them higher utility. And we require our selected committee to be fair to all subsets of voters. This general idea dates back more than a century and has been extensively studied. So concretely, we define the stable committees in the following way. Given any two committees S1 and S2, the pairwise score of S2 over S1 is the number of voters who strictly prefer S2 to S1. And given a committee S of weight at most k, we say that a committee S prime blocks S if the fraction of voters who prefer S prime to S is at least the fraction of weight of S prime over the weight limit k. Or equivalently, we can write this. And we say committee S is stable if there is no blocking S prime. So here's an example. This is the set of voters, and here's a possible committee. And here's a subset of voters. So if for some subset of voters, there exists a smaller committee of proportional sets, so that each person in this subset of voters strictly prefer the smaller committee to the larger committee, then we say that the larger committee is unstable. And the model has a fair taxation interpretation, where each voter pays some same amount of tax towards buying committee members. And in this interpretation, any coalition of voters T can buy a committee of weight T times K over N. And in this case, we require that no coalition of voters can spend their own tax money better, so that each one in the coalition are better off. In the previous paper, we actually showed stable committees may not exist. Here's an example. There are 6 voters and 6 candidates, and we are allowed to select at most 3 candidates in our committee. And for the preference model, we assume each voter ranks all the candidates and then ranks the committees by the best candidate in each committee. And the instance is as follows. The first voter thinks A is better than B, better than the rest. And the second voter thinks B is the best and C is the second best. And the third voter thinks C is the best and A is the second best. Similarly, we have the preference profiles for the other 3 voters. And now we focus on voter 1 and voter 2. Since voter 1 thinks B is the second best and voter 2 thinks B is the best, we know that A or B must be chosen in any stable committee. Otherwise, voter 1 and 2 can deviate and select B. And because 6 voters can select 3 candidates, proportionally 2 voters should be able to select 1 candidate and deviate. And similarly, by looking at voter 2 and voter 3, we know B or C must be chosen in any stable committee, because otherwise 2 and C can together select C and deviate. And by looking at 1 and 3, we know A or C must be chosen in any stable committee. So to summarize, we know that among A, B, C, at least 2 of them must be in any stable committee. And similarly, by looking at 4, 5, and 6, we know that any stable committee also has at least 2 out of B, E, and F. Therefore, any stable committee must be of size at least 4. So there is no stable committee of size K equals 3. And to bypass this impossibility result, we have the following 2 ideas. One is to define randomized committees, and the other is to define approximate stability. Also in our previous paper, we defined the stable lottery, which is a randomized stable committee. We say a distribution delta over committees of weight at most K is stable if for all committees S prime. In expectation, the number of voters who prefer S prime to S is less than the proportional size of S prime times N. So here's an example of a lottery. So a pizza is $10 and a puzzle is $20, a printer is $30, and we are allowed to spend $40 on them. So a valid lottery is as follows. We randomize over selecting a pizza and a puzzle, or a pizza or a printer. But the following is not a valid lottery by randomizing over pizza plus puzzle and puzzle plus printer, because sometimes we spend more than our budget. And another idea is to have this approximate stability. So a committee of weight at most K is C approximately stable if for all committees S prime, the number of voters who prefer S prime to S is less than a constant C, times the fractional weight of f prime times n. And similarly, we can define the approximately stable lottery by taking the expectation of left-hand side. And the main result of our paper is this. A 32 approximately stable deterministic committee always exists. And to show this, we first show the existence of approximately stable randomized committees, and then construct a deterministic solution using the randomized solution. So here's our first step. We want to show there is always a 2 approximately stable lottery. This problem has a duality view as follows. We view the stability problem as a zero-sum game. So we choose a defending lottery, delta D, and some adversary chooses an attacking strategy, delta A. We want to prove that the following thing holds. That we can select some lottery delta D, so that for any attacking strategy as A, in expectation, the following value is less than 0. And because this is a zero-sum game, we can actually swap max and min. So given any attacking strategy, it can be randomized. We want to show we can select a deterministic defending strategy so that in expectation, that value is less than 0. Okay. So we want to show there is a 2 approximately stable lottery. And that is given any attacker strategy delta A, we need to show there exists a defending strategy with weight at most k, so that in expectation this is less than 0. And we let B to be this value in expectation. So equivalently, we can show this the expectation of the number of voters who think the attacking strategy is better than the defending strategy is at most 2B. So the first attempt is the following. If some attacking strategy is chosen with probability Pi in the attacking mixed strategy, then we select this committee into our defending lottery independently with probability Pi over 2B. And for any voter, we suppose she likes some committee S1 better than S2, better than S3. And we want to show the following thing holds. So here's the proof. We write xi to denote whether si is chosen in the defending strategy SD. So the probability that B prefers SA to SD equals the sum over I, the probability that the attacking strategy is just Si, and all the better defending strategies aren't selected. And because the probability that SA equals Si equals Pi, we can rewrite the previous line as this. And then because our procedure is to select each Si with probability Pi over 2B, we can further rewrite the formula to this. And that equals the following thing, sum over I 2B times Pi over 2B times the product of J being at most I1 minus Pj over 2B. And that should be less than 2B. So now we have shown the inequality holds. But the problem of this rounding procedure is that the size of SD sometimes may exceed this K. But because its expected weight is at most K over 2, we can actually use some dependent rounding procedure to ensure that the weight of SD never exceeds K. And by doing this, we get negative correlation instead of independence, but the previous analysis still works. And now our problem is to convert the randomized solution into a deterministic solution. So we already know that for any instance, we have a two approximately stable randomized committee delta. And we write this xi to be the probability that delta realizes to si. And in the following analysis, we assume each xi is small, but that is not essential in our analysis. We say that a voter considers S good if S is within top 3 quarters in her preference profile, measured by this delta. That's the definition of good. And we have the following two observations. The first is any committee SA is considered good by no more than 8 times the weight of SA or K times N voters. Because otherwise, we know SA is preferred to delta by at least 2 times WSA over K times N voters in expectation, because the definition of good is S is within top 3 quarters in her preference. And since SA is preferred to delta by that many voters in expectation, we know delta cannot be too approximately stable by our definition. So that is a contradiction that shows the statement that any committee SA is considered good by no more than that many voters. And the other observation is there is a committee SD considered good by at least 3 over 4 times N voters. And we can show that by just pick a random committee from this delta. So in expectation, at least 2.75 N voters consider this random thing to be good. So we have these two observations, and our algorithm is as follows. So this is the set of voters, and we know there is a committee SD considered good by at least 3 quarters of them. So we pick that committee into our solution as one. Now, at least 3 over 4 fraction of voters are satisfied by having a good committee. Now we recurse on the unsatisfied voters. And by recursion, now the new number of voters is at most N over 4. And we set this new budget limit K prime to be K over 2. And now we have another committee that is considered good by at least 3 over 4 fraction of voters in this unsatisfied region. And we pick this new good committee as 2 into our solution and satisfy another 3 quarters of voters, and so on. So this is our recursion. And we know if we set the first step budget limit to be K over 2, then the total limit should be less than K. And we have the following observation. For any committee SA, the number of voters who consider it as a good in at least one step in the recursion must be an upper bound on the number of voters who consider SA to be better than the committee that the algorithm selected. And we also know that this amount is at most 8 times WSA over K over 2 times N times 8 times WSA over K over 4 times N over 4, and so on by our recursion process. And so we know that sums to at most 32 times WSA over K times N. And by this time, we have successfully proved that a 32 approximately stable committee always exists. So here are some open questions. The first is, does deterministic exactly stable community always exist in some more specific settings? In particular, the following question seems to be interesting. So the setting is called unweighted approval set, where each voter approves a subset of candidates, and she ranks committees based on how many candidates she approves. And the candidates are unweighted, so we are allowed to select K candidates. And the question is, does an exactly stable committee always exist? There's also a question of whether exactly stable lotteries always exist. And also, can we get better constants in this problem? In our paper, the lower bound is 2 and the upper bound is 32. So can we get a better upper bound, for example? And another question is whether we can compute stable committees efficiently. In our paper, our results are for existence instead of computational. So that's all. Thanks for your attention.